Hello, in this video I will show you one difficult proof, and the difficulty will be in the fact that you will have to apply some trick in order to be able to transfer from t of n to t of n plus 1. Let's start. A difficult proof, problem number 6, and this problem was already present in the Pre-Calculus 1 course, and there it was formulated as problem 15, and this is the formulation here. We have to show that the following formula holds for all real numbers a and b, and for each positive integer number n. And here is the formula. And in this course Pre-Calculus 1, it was proven without induction. First I wrote how this formula looks for n equal to 1, 2, 3, and so on and so on. And there I just wrote down the proof, where I started from the right hand side of the formula and simply performed parenthesis multiplication, and I got a lot of cancellations and I arrived at the left hand side. But now I will prove it with help of induction. And here, in order to understand what is happening here in this parenthesis, for this it is really most practical to write it down with a sigma notation. So what is happening here actually? You see that in this parenthesis we have some products of a times b, and a or b are in some power. And you see that first we have a to n minus 1, and then in the next term the exponent at a is decreasing and the exponent at b is increasing. So you can say that in this first term here we actually have a to n minus 1 times b to 0, right? Then we have a to n minus 2 times b to the first, and then the entire time the exponents at a are decreasing, exponents at b are increasing, and the total sum of the exponents is at each stage equal to n minus 1. So we can actually write down this expression in the parentheses with help of a sigma notation. So it will be the sum with k going from 0 to n minus 1. So a will be 2 n minus 1 minus k, and b will be 2k. So the exponents at b are increasing from 0 to n minus 1, and exponents at a are decreasing from n minus 1 to 0. So if you look at this sum here in this way, you will also understand very well that you have n terms in such a parenthesis, n terms in the parenthesis. Okay, and this makes also easy to write down t of 1, because what is t of 1? T of 1 tells you that a to the first minus b to the first is equal to a minus b times, and in this parenthesis you have just one term, and this term is equal to a to the power 1 minus 1, which is a to 0, which is simply 1. So we get indeed that a minus b is equal to a minus b, which is true. So this is done, and now in this proof we fix our numbers a and b, and we perform induction for n. So a and b are fixed now, and we formulate the thesis for n plus 1. And what will it be? It will be that a to n plus 1 minus b to n plus 1 is equal to a minus b, and now in this parenthesis the sum of the exponents must be equal to n, because, well, in the thesis for n the sum was n minus 1, so in the thesis for n plus 1 it must be equal to n. So we will get first a to n, then a to n minus 1 b, and so on and so on. And at the end we will have a times b to n minus 1 plus a to 0 and b to n. So this is our thesis for n plus 1. And so we must show this statement, provided that the statement for some n is true. Okay, so now this will be this induction step in which we will have this difficulty, because we will have to perform some trick in order to be able to use this assumption for n. So now assume that t of n is true for some n greater than or equal to 1. Show that with this assumption also t of n plus 1 is true. Okay, so now I have assumed that my t of n is true, so that the formula is true for n, and I have to show that this formula is true for n plus 1. So this is what I will do. I will do like this. A to n plus 1 minus b to n plus 1 is equal to. And now I will do some trick which will allow me to make this transition from the formula for n to the formula for n plus 1. So what I will do is the following. I will subtract and add the same thing. It is perfectly okay to do so, because by adding and subtracting the same thing, I do nothing. I just perform a zero operation, right? So this is what I will do. I will subtract a to n times b, and I will then at once add it back. A to n times b. And then I still have a minus b to n plus 1 from my formula. So this here is a zero operation, right? Nothing happened. Zero. So it's a zero operation. It doesn't change anything, but it means a lot to me, because now I will be able to apply my induction assumption when I group together these two. And, well, I also group together these two here. So what is happening with these first two? I can factor out a to n, and I will get here a minus b. This is the first part. And in the second part, I will have, I factor out b, and in my parentheses, I will have a to n minus b to n. And for this guy here, I can apply the induction assumption that this formula for a to n to b to n is this one here. Okay, so now the first one is simply unchanged. It is like this. And the second one here, I will apply the induction assumption. Induction assumption that this a to n minus b to n is equal to a minus b times this entire expression here, right? A to n minus 1 plus a to n minus 2b plus ab to n minus 2 and b to n minus 1. And now we are just one step from success. Because you see, we have here a common factor in these two parts of our sum, and this is the common factor which also appears in this thesis here for t of n plus 1. So now I factor it out, and I gather together everything what is multiplied by this factor. So from this first expression here, from this first term, I will get a to n. And then another color, maybe this one. From this second one, I get here b times a to n minus 1. And this is exactly what I'm supposed to get here, you see? So this is a to n minus 1 times b. And then another color, I will have here the next one will be a to n minus 2 times b, so it will be a to n minus 2 times b squared, and so on and so on. Now I will just use the regular color, and at the end we will have a b to n minus 1 coming from this guy multiplied by b, and the very last will be, this will get the red color because it's just the last one. Here b to n minus 1 times b gets me b to n. And this is exactly what I was supposed to get. This is exactly my t of n plus 1, which is standing here in my iPad above. So then this usual stuff with the principle of mathematical induction. The principle tells me that this formula indeed is true. So this was a difficult one. Thank you for watching. Bye bye.